Morning, everyone, and thank you for joining us. I'm Yan Song, incoming assistant professor at the University of British Columbia, Vancouver, BC, Canada. On behalf of the organizing team, I'm pleased to welcome you to the Spatial Temporal Statistics and Data Science Online seminar series. This series brings together professors, researchers, practitioners, and students worldwide to explore methods, theory, and applications of space-time data. Our goal is to provide an avenue to share ideas and to spark conversations that push the field forward. We are grateful for the support of the ASA section on statistics and the environment, the Royal Statistical Society's Environmental Statistics section, and the International Environmetrics Society, whose communities help broaden the reach and the impact of this series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them after the presentation during the discussion period. All talks are recorded, and the recordings along with the slides will be posted on our website. We typically host 1 to 2 seminars each month, and you are also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you will find those details as well as other resources at stsds.org. With that, I will turn it over to my fellow organizer, Yan Gong, to introduce today's speaker.
Hello, everyone. I'm also Yan. I'm visiting assistant professor at Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi, and I'm also co-organizer of our STSDS seminar series. Before I introduce today's speaker, I'd like to take a moment to highlight our upcoming presentations, which you can see on the slide. So next year, January, February, and March, there will be 3 talks from our community. The first one is on online stochastic generators using spleen basis for regional bivariate wind sample from ERA5 with Dr. Song. And the second talk will be from me on causal spatial quantile regression in February. And in March, Professor Jian Cao will talk on scalable learning for censored Gaussian processes based on conditional independence approximation. We also invite you to nominate future speakers for our series. You can do so at the link as shown on the slide. You can basically find it on our website. Now, I will be very happy to introduce today's speaker, Jordan Richards. Jordan is based at the University of Edinburgh, where he is a lecturer in statistics and director of the Center for Statistics. He received his PhD in statistics and operational research from Lancaster University in 2021, before joining KAUST for a 2-year postdoc. Jordan's research interests include extreme value theory, spatial statistics, statistical machine learning, and Bayesian data analysis. With that, I'm happy to turn it over to Jordan to begin his talk. Jordan.
Nice, thank you, Georgie, for that very kind introduction that I definitely didn't write myself. Right. Which makes me sound a bit more successful than I am. Can you see that okay?
Yes.
Yeah, nice. Okay, so today I'll be talking a bit about fast and amortized inference for spatial extremes using neural Bayes estimators. Now, this is really a collection of a few papers, 2 of them methodological, that I worked on during my postdoc at KAUST. And that was with predominantly with Matthew Sainsbury Dale, who's a postdoc currently at KAUST. Pictured here on the slides there are me and him in the desert somewhere in Saudi Arabia, looking pretty cheerful. Matt is, he is really the mastermind between the neural Bayes estimators project, and you'll see his name appears quite frequently in these slides. And so I worked on a couple of papers with Matt, also in collaboration with Raphael Huser at KAUST. He was my postdoc advisor and Matt's current postdoc advisor, and Andrew Zamit Manjian, who was at the University of Wollongong at the time. So I'll talk a bit about a couple of methodological papers with them. My most recent sort of experience with neural Bayes estimators is less on the methodological sort of work and more on using neural Bayes estimators in comparative studies of essentially Bayesian inference techniques for scalable modeling of spatial extremes. And so I'll talk briefly a bit about a current piece of work with some of the collaborators on the screen here. So from left to right then, Rita Majumdar from the University of Arkansas, Emma Simpson from the University, from UCL London in the UK, Ben Lee from George Mason University, Likun Zhang from the University of Missouri, and that's me on the right. Okay, so what is this talk about? I mean, the title is Fast Amortised Inference for Spatial Extremes Using Neural Bayes Estimators, which contains a number of buzzwords that I'll explain as we go along. The talk, okay, my interest is really in spatial extremes, but the takeaway message that I want you to have from this talk is that really this work is not for people interested purely in extremes or in spatial statistics. It's not really for people interested in using neural networks or people interested in doing Bayesian inference. Really what I want you to take away from this talk is that the methods that I talk about are really for anybody who's interested in estimating things. So specifically people who are interested in estimating models that take too long to fit, to do inference for, or require repeated fits. So maybe you might want to fit a model that's laborious in an online fashion, or when you want to do some sort of uncertainty assessment, you have to do maybe a bootstrap, and then you have to do these repeated fits. And so hopefully the methods we talk about really are going to help speed up those inference times. Okay, so an outline then for today's talk. I introduce neural Bayes estimators, and then I talk about two specific papers. So neural Bayes estimators for irregular spatial data. So that's really the core spatial stats part of the talk. And then I talk about neural Bayes estimators for censored data, specifically for peaks over threshold models that are very popular in the spatial extremes literature. And then if I have time, which potentially I might not do, I'll talk about this comparative study of scalable Bayesian inference methods for spatial extremes. Okay, so the motivation then, what are neural Bayes estimators? So first I want to talk a little bit about likelihood-free inference. So hopefully as statisticians, you're familiar with the likelihood function. Typically statistical inference, whether or not it's frequentist or Bayesian, it proceeds via some likelihood function, right? Either you're optimizing it or you're using it to help you draw posterior samples. However, the likelihood function may not necessarily always be available. If you have sort of quite complicated generative or simulator models, it can be quite difficult to derive the likelihood function at all. It might not be something you can write down, or it could be computationally intractable. And this is quite a common problem in the spatial extremes literature. Things like max stable processes, which are a popular model for spatial extremes, they don't have a tractable likelihood function when the dimension of the problem increases moderately above about 10 dimensions. And as we'll see a bit later on, there is this common procedure of using censored likelihoods when doing inference of spatial extremes that just makes essentially full likelihood inference almost impossible. And even when you do have the likelihood function, if it is computationally intractable, maybe you can get around that by approximating it. I might talk a little bit about composite likelihoods, pseudo likelihoods, or approximate Becker approximations for likelihoods in this talk. Of course, if you're going to approximate the likelihood function, you then have this trade-off between sort of the computational efficiency gains and the statistical efficiency losses that you might experience by approximating that likelihood function. So one way to get around these issues that arise when using likelihoods is to do likelihood-free inference. You could, for example, use methods from ABC, so approximate Bayesian computations, or an alternative is a class of estimators called neural estimators. So what is a neural estimator? It is a neural network that takes in some data Z as an input and provides a parameter point estimate theta as an output. Now, can everyone see my mouse, by the way, if I'm sort of wiggling that around? We've got some nods.
Yes.
Yep.
Yes.
Nice one. Okay, thank you. Yeah, so we have here denoted by theta hat then. This is our neural network. It takes in data Z as input and it'll just spit out a parameter point estimate as its output. Now, neural estimators are really straightforward to construct, to build. And what we do is we sample many parameter vectors theta from some prior distribution capital pi. Conditional on those, we simulate some data Z. And then we train a neural network to map from that simulated data to parameter point estimates by minimizing some loss function. And if we construct estimators, neural estimators in this way, what they are doing really under the hood is targeting what are called Bayes estimators. So a bit of background on Bayes estimators and sort of Bayesian decision theory then. We start with a non-negative loss function, here denoted by L. And what this does is this takes in two inputs. We have our parameter vector theta, the parameter point estimate from the estimator, and the loss function is essentially going to quantify how good our estimate is, how close it is to that true value. And I'll give some examples of these types of loss functions that we might use in a couple of slides' time. Now, when we're working in a sort of a Bayesian framework, what we want to do is we don't want to minimize this loss function for a single parameter vector, a single data set. We want to minimize this loss function so that our estimator works well on average. And we do that by creating an estimator that minimizes what's called the Bayes risk. So essentially, it is the average of the loss function over all possible realizations of the parameters and over the sample space as well. So over all possible realizations of our data. Okay. Now we call an estimator that minimizes this Bayes risk the Bayes estimator with respect to this particular loss function and the prior distribution that we've placed on theta, on the parameter vector. And our Bayes estimators, they have some nice optimality properties. They're asymptotically efficient. They're consistent if you make judicious choices about the loss function. And essentially, they're nice. They work really well on average. And what we're going to do is we're going to construct a neural estimator that targets this Bayes estimator. So if I represent my estimator theta hat as a neural network and parameterize that neural network by sort of the standard buzzwords of weights and biases, and I find those optimal weights and biases that optimize this empirical risk problem. So let's look at this a bit more closely. If I say draw capital K parameter vectors theta k from my prior, condition on those, sample the data zk, and then I take the average of the loss function and find the weights that optimize that average, and then I will have constructed a neural estimator that targets the Bayes estimator, and we refer to that as the neural Bayes estimator. Okay. Now, optimizing these neural networks, I'm not really going to talk about. It's sort of standard deep learning type machinery, and we use things like stochastic gradient descent and the Adam optimizer to do this. Really, what I want to talk about is the choice of the neural network that we're going to be using, which is going to be dependent on the data, the modality of the data Z that we're going to be working with. So my colleagues in this really nice paper in the American Statistician from 2024, they did all the nice theoretical work that showed that these neural Bayes estimators, if they're constructed in this way to approximate Bayes estimators, then they inherit the nice attractive properties I've already really talked about. Okay, so consistency and asymptotic efficiency and these optimality conditions. Now we have different choices of the loss function that we can pick, and the choice of the loss function essentially specifies the part of the posterior that we're targeting with these point estimates. So if we take the loss function to be the absolute error loss, then our neural Bayes estimator will be targeting the posterior median. With the squared error loss, it's the posterior expectation. And if we use things like the quantile loss or the pinball loss, then these neural Bayes estimators are going to be targeting the posterior quantiles. And we can parameterize that loss function by say, a quantile level tau. In that case, the neural Bayes estimator will approximate the posterior tau quantile. And we also showed in a nice piece of work, myself and Georgie, with some collaborators from CALS, that you can use weighted versions of these quantile loss functions as well. What we show in this nice paper in Extremes was that you can build these neural Bayes estimators that target conservative estimates of high quantiles or what are called return levels in the extremes literature. Okay, but I won't be talking too much about that today. So you can pick these loss functions, you can chain these loss functions together as well. So I can construct a loss function that is the summation over multiple loss functions. In this case, I'm summing over p quantile losses. And in this way, what I can do is I can construct neural estimators that target a vector of marginal posterior tau quantiles. And so I can, a bit later on, construct a neural Bayes estimator that targets the 95% credible interval. Okay. Now, one of the properties of Bayes estimators that we really want to make sure our neural Bayes estimators satisfy is permutation and variance. So if I have replicates of data Z1 up to Zm, and they are conditionally independent given the true parameter vector theta, then the Bayes estimator must be permutation invariant. So what that means is if you, say, have an application in spatial extremes, it's very, very typical to assume that spatial replicants are independent over time. And if I permute those replicates, my Bayes estimator should produce exactly the same parameter point estimate. And construct a neural Bayes estimator that satisfies this property. This is done using a framework called deep sets. Now, deep sets are a type of permutation invariant neural network. In essence, if it is as it says on the tin, if I permute my replicates, then the answer is the same. Now, it has this mathematical formulation. This makes a lot more sense when I show the schematic on the following slide. We have our ZIs. These are our data independent replicates. These pass into what's called the inner neural network psi. That then gets aggregated by this function A. This is a permutation invariant aggregation function, something like the mean or the maximum, which will always give the same answer regardless of the permutation of the inputs. And then this sort of aggregated data then passes into this other neural network, this outer neural network phi. So it looks a little bit like this. So this is the general setup for what's called a neural Bayes estimator, particularly within the neural estimators R package and Julia package, which I'll touch upon at the end. So we have our Z1 up to Zm, they pass into phi. And these phi, this is exactly the same neural network. It shares parameters or weights and biases. And then the outputs of these pass into the permutation variant aggregation function A. We have some summary statistics T, and then they're then transformed again via another neural network. And then this will spit out a parameter point estimate. And that point estimate will be targeting parts of the posterior that our loss function has decided upon. Now, this neural network at the end, this T, this will always be a vector of summary statistics. So this neural network here will always be what's called a densely connected neural network. It will be a multi-layered perceptron. But we can make choices about the architecture of psi, dependent on the modality of Z, dependent on the type of process model that we're actually generating data from. Now, sort of a typical choice you might want to take is again, a dense neural network, a multi-layer perceptron. These work well if you have univariate or multivariate data, but you can make more efficient choices if you have sort of spatial structure in the data that you're working with. So if Z is regularly gridded data, so spatial data that's represented as an image, this inner neural network we can represent as a convolutional neural network. It's going to extract spatial patterns in the data that are going to make our neural Bayes estimator much more efficient. And when I talk a bit about neural Bayes estimators for centered data, this is the type of neural network that we'll be using. However, there are some limitations to using this neural network. It requires your data to be measured fully observed on a regular spatial grid, and it can only be used with grids of a single size. And one of the really nice things about neural Bayes estimators and neural estimators in general is they're amortized. So I don't necessarily need to retrain my estimator every time I want to apply it to a new data set. However, if you're using a convolutional neural network, CNN is wedded to a specific spatial grid. So I would have to redesign and retrain my estimator if I observe new spatial data on a new regular spatial grid. And so that was the motivation with this first piece of work I want to talk about, where we replace the convolutional neural network with a graph neural network that is amortized with respect to the spatial configuration and the number of spatial sampling locations you have. And so you only have to build one estimator that can be applied with any new spatial data set. Okay. So we build a neural Bayes estimator for regular spatial data using the graph neural network. A graph neural network you can think of really as an analog of a convolutional neural network for graphs. So rather than performing convolutions, discrete convolutions on images, they perform local convolutions on graphs. So what you can think about doing is representing your spatial data as a graph. You might think about every sampling location as being a node in that graph, and you might construct an edge or an adjacency matrix that is somehow weighted by the spatial sampling, the distance between the spatial sampling locations. Now, graph neural networks, I won't go into the sort of technical details of these. If you know, you know, but essentially what they do is they help to model spatial dependence in graphs. And one of the really nice things you can do with these graph neural networks is set them up in such a way that they're not dependent on the number of spatial locations, the number of nodes in the graph. Okay, so you can build neural Bayes estimators that are amortized with respect to the spatial sampling locations. So it looks a little bit like this. You can imagine we have here on the left-hand side then our spatial data. This is our Z1 up to Z4. I have a single replicate of this in this schematic, and you can think of having 4 sampling locations. And what I do is I just represent that spatial data as a graph. You can see I have Z1, Z2, Z3, Z4. These would be the data observed at my sampling locations, and I've built an adjacency matrix that determines that graph. Potentially, I might weight the edges in this graph by the distance between these sampling locations. Now, the type of graph neural network we're using, it's a sort of fairly bespoke architecture. It has what we call a propagation module that does all the spatial dependence learning, and then a readout module that has a fixed output length. So here you can see I have capital H hidden layers in my graph neural network. I provided on the slides actually the formulas for the convolutions that are being performed. It is a bit technical, but I'll quickly go through this. So in this part of the propagation module, what I'm doing is taking a weighted sum of the summary statistics observed at that particular node. So for example, here, this would be at the first node in the hidden layer, in the hidden graph in the first layer. What goes on here is this would be, for starters, a weighted sum of the vector observed at this node, and then a weighted sum of the vectors at all of the other nodes in the graph as well. Okay, and we can weight the contributions of the vectors at the other nodes using a weighting function here. This weighting function we actually represent as a multi-layer perceptron in the neural estimators package. And what we have at the end, so this propagation module, this does all the spatial dependence learning. But of course, I mentioned that this outer neural network, this is a densely connected neural network, a multi-layer perceptron. It acts on vectors of data. And so what we do is we have this sort of aggregation of the information. We sort of flatten all of the information at each of those nodes into a single vector. You can see here R1 up to R5. And this would be then what passes into the permutation invariant aggregation function, and that then goes on into the neural network, and we get our parameter point estimate as an output. Now, of course, there's a lot of technical details here. If you're really interested in the deep learning aspects, I recommend you you go away to the paper. What I really want to show you is that these things work incredibly well in practice and can be very, very useful if you want to do inference for spatial applications. Now, one of the key sort of novelties of this work was that, well, we wanted to build these estimators that are amortized with respect to the spatial sampling locations. Of course, a priori, before you observe data, you're never going to know what those spatial sampling locations are going to look like, what that configuration might possibly be. So as part of the training scheme for these graph neural network-based neural Bayes estimators, we randomly generate the spatial locations at which we observe data and optimize, and well, we place a prior on these, and we include that within the training scheme. So you generate spatial sampling locations, you then generate the parameters theta from the priors I've described previously, and then you generate now your spatial data conditional on the true parameters theta, but then also on the spatial sampling locations that are being treated here as random. Okay, so I placed a prior omega on the sampling locations. This now features in the Bayes risk that we're going to want to optimize via this empirical risk minimization problem. Okay. And in the paper, we have this really nice theorem that says that actually for Bayes estimators, these are invariant to the particular choice of prior that we place on the sampling locations. Okay, so it doesn't matter whether or not we place an informative or a vague prior on the sampling locations. Yeah, if we train our neural Bayes estimator for a long enough time, if we produce enough training data for optimizing those weights and biases, it doesn't really matter. The quality of the estimator that we get out at the end isn't affected by the choice of prior. So we choose to generate these random spatial sampling locations using the Matern cluster process. I won't really go into the details of these, but here you can see on the slide some examples of what these might look like. They are a Matern cluster process is parameterized by an intensity and a mean parameter, lambda and mu. And through choices of these, you can get this nice clustering of spatial sampling locations that you might see in some applications. As you increase lambda and decrease mu, you essentially get to this sort of setting where the sampling locations are essentially uniformly distributed over the particular sampling domain that you might be working with. Okay, so just to illustrate proof of concept that this graph neural network-based neural Bayes estimate works incredibly well in practice, and it is competitive with sort of standard, like the gold standard Bayesian inference approach. We set up a simulation study where we were generating data from a Gaussian process. In this case, a single replicate. I'll talk about multiple replicas when we move on to the spatial extreme setting. But here we just have a Matern Gaussian process, which is parameterized by two parameters, the standard deviation sigma and a range parameter rho. And in both of these cases, I place uniform priors on these sort of things. This graph neural network based estimator is trained on a GPU. Can't quite remember exactly how many training samples we used to optimize this, but it did take about 24 minutes to optimize. And what we're going to do is we're going to compare our neural Bayes estimator against the map estimator, which is found by optimizing the posterior. So this you can think of as being an analog of the posterior mode. And what we do is we train this neural Bayes estimator to be amortized with respect to the sampling locations. So I'd randomly generate the sampling locations during training, and then I'm going to test this out of sample using some specified sampling locations pictured on this top row. So I have these 4 test sampling locations that weren't used within the training of the neural Bayes estimator. So I have data observed on these uniformly generated sampling locations, and then I have these sort of pathological examples where I have, you know, these sort of squares of sampling locations, and I generate data at these, and then I see how well my neural Bayes estimator can estimate those two parameters, the standard deviation and the correlation. And what we see from the empirical marginal sampling distributions given by these box plots is it does extremely well. Okay, so we see very little bias in the neural Bayes estimates for the, in this case, the posterior medians of the standard deviation and the range parameter. In a lot of cases, it has lower variance than the map estimator, which is given here in yellow. The neural Bayes estimators are given in green. And this is data, these results come from training a single estimator, right? So I have one neural Bayes estimator that I can then feed these data into, and it spits out a parameter point estimate. Whereas for the map estimator, I have to optimize this for each new data set. Okay, so I have to optimize this 4 different times, whereas for the neural Bayes estimator, it is one estimator that is then extremely quick to query.
Sorry, I have a question about the previous slide. So I'm a bit curious about the architecture of the neural Bayes estimator here, and specifically where does the graphical neural network come into play?
Okay, so yeah, if I just go back to this point here, so the particular sort of architecture we have in this case is this inner neural network is a graph neural network. So our data is represented as a graph, and then we perform graph convolutions over this neural over that graph. The architecture is not it's not an off-the-shelf architecture that we're using. It's this particular architecture that we've designed. So we perform local convolutions, and then you have this is essentially what you would call a skip connection in the graph deep learning literature, and then some sort of weighted average of these points. If I remember correctly, I think this particular architecture had 2 or 3 hidden layers. I can't quite remember which one it was, but that was optimized as part of the simulation study. If you want sort of like exact details, I would recommend going to have a look at the paper. Does that answer the question?
Yeah, thanks.
Yeah. Nice. Okay. So in terms of accuracy, both the neural Bayes estimator and the gold standard map estimator have similar root mean squared error, but where the neural Bayes estimator shines is in its computational the computational gains. Okay, so this was a fairly sort of simple example with a small data set, you would say. So the map estimator doesn't take particularly long to get. It takes 1.2 seconds, but the neural Bayes estimator has a 600-fold speed up. So querying the neural Bayes estimator takes 0.002 seconds. What I will say as well is this map estimator, there is some sort of variation around this value, right? So, it's not a deterministic time it takes to get a map estimate out. It's dependent on the data at hand. Whereas for the neural Bayes estimator, this is a deterministic time. Okay, so we just feed this the data into the neural Bayes estimator, and it provides a parameter estimate almost immediately. We also looked at the empirical coverages of these things. So in this case, these parameter estimates correspond to the posterior median, but we can also design a neural Bayes estimator that targets the 95% credible interval using that chaining of tilted loss functions I described earlier on. We did that and we looked at the empirical coverages in this simulation study. In both cases, the neural Bayes estimator provides basically nominal coverage, so 94.6% for the standard deviation parameter and 95.2% for this correlation parameter, this range parameter. And moving on quickly then to a real data example. So we had some sea surface temperature data observed from this particular satellite, the MPP weather satellite. And we had, tens of thousands of these observations across the entirety of the globe. And what we decided to do with these data was use a local moving window approach. So to deal with the non-stationarity that you would find in sea surface temperatures, we discretized the globe into these hexagons. And within each hexagon, we have a number of sampling locations, and we fitted a Matern Gaussian process to each of these sampling locations. So this is where a neural Bayes estimator begins to shine. because not only are we doing we're not doing a single fitting of a single Matern Gaussian process to the entire data set, we're fitting multiple Gaussian processes, I think a couple of thousand in total across each of these different hexagons. And now within each of these hexagons, we had roughly between 2,000 and 12,000 sampling locations. But we're only going to have to build one neural Bayes estimator. So as I mentioned a bit earlier on, the neural Bayes estimators using graph neural networks, they're amortized with respect to the configuration and number of sampling locations. So even though each of these hexagons had a different number of sampling locations, we could still use the same neural Bayes estimator to get out the estimates for our Matern Gaussian process. So yeah, we had 2,000 Matern Gaussian processes that we did inference for. In total, it took about 3 minutes on a single GPU to get all these estimates out, so incredibly fast. There's no requirement for doing MCMC here, right? So, you know, we don't have all these problems related to choosing proposals or doing burning, picking the number of chains that you want to generate. The data goes into the neural Bayes estimator. We get parameter estimates out almost immediately. That's what the top row is. So posterior medians of the range parameter, standard deviation. There is a nugget variance in here as well, which I believe is this one on the right hand side. And then also credible intervals as well. Okay, so I should specify here there are two types of neural Bayes estimators. They're Bayes estimators with respect to the loss function. So in the top row, the neural Bayes estimator is trained with the absolute error loss function. These are posterior medians. Bottom row would be posterior credible intervals. Okay. So incredibly fast spatial application. And that was really nice. And that was a piece of work that was published in the Journal of Computational Graphical Statistics earlier on this year. And in parallel with this work, we were also working on building neural Bayes estimators for sensor data. Now, why might we do that? Well, if you're interested in doing inference for spatial extremes, you might, and this, you know, if you talk to people outside of the extremes literature, they might find this a bit pathological, but you might actually choose to treat your data as centered. So even though it's going to cause you some computational strife, it's been shown that it can be quite a useful tool to treat your data as centered if you have spatial data, you're interested in learning about spatial extremal dependence, for example, and you have observations that are marginally not extreme, then these can bias estimates of the spatial extremal dependence parameters. And this sort of bias can be mitigated in what's called a peaks over threshold type framework. So this is essentially artificial censoring. What you do is at each of your sampling locations for each component of your random vector, you set a censoring threshold. If a point is below that threshold, you treat it as censored, so not fully observed. And if it's above that threshold, you treat it as fully observed. So I'll show an example of this in a two-dimensional case in just a few slides' time. Okay, so you choose a censoring level, and this is typically done. The center threshold is typically taken as a marginal quantile. So for each component of my random vector, I will pick its TALF quantile with TALF close to 1, and I will treat that any point below that threshold as centered. So in this particular example, I have a realization of a Gaussian process. And what I'm doing is just taking a scatter plot. I'm looking at two locations. I have Z1 and Z2. Now, if really what I'm interested in doing is learning about spatial extremal dependence, I'm interested in learning about the extremal dependence in this top right-hand square up here, okay? And so what goes on down here in this lower left-hand part of the space, I'm not really that interested in. So what I'm going to do is I'm going to set these two censoring thresholds, C1 and C2. So C1 for component 1 and C2 for component 2. And then when it comes to setting up the likelihood function that I'm going to be working with, then the contribution of a data point to that likelihood function differs depending on what part of the space the point lies. So if both of my components are extreme and I have an observation, one of these red points in the top right-hand orphan, then my contribution of those points to the likelihood function is just the usual contribution, the joint density of those observed points. In a case where only one of those points is extreme, so in this case you can see marginally Z1 is extreme for these blue points, what I do is I treat the second component Z2 as censored in particular below that threshold C2. So what I do is I record this information in this one hot encoded vector I. So this just takes values 1 if Z2 is less than C2 and 0 otherwise. And then my contribution to the likelihood function of a point that lies in this space is this integral over the joint density. So I'm marginally integrating out the contribution of Z2. So I'm integrating below the lower endpoint of the margin for Z2 up to that centering threshold C2. Okay. And in the case whereby both of my components are not extreme, I'm going to be integrating both of those out. So here, these points, I would record that information in one hot encoding vector I1 and I2, and then the likelihood contribution of these particular points is just the integral of the joint density function over that space. Now, what we can see here is, regardless of the actual observed values of these purple points, their likelihood contribution is exactly the same. So this integral is going to have exactly the same value regardless of where that point lies in that space. Okay. And that's an example of sort of this type of centering that would occur in a d is equal 2 setting. These sort of aspects extend quite naturally to higher dimensions d. And hopefully you can see that as the dimension of the problem grows, the likelihood function is going to become very, very quickly computationally intractable. Okay, and evaluation of that likelihood function is going to be very, very expensive for applications of spatial streamal dependence models. So the motivation for this particular piece of work was that what we wanted to do was build these neural Bayes estimators that bypass evaluation of this centered likelihood. They would be able to be used for inference for peaks over threshold spatial streamal dependence models, and they mimic this peaks over threshold type inference approach. And just a quick note here then, this centering scheme that we're applying, this is something that a modeler knows a priori, right? So this is not any form of random centering. This isn't a missing data type problem. You need to know what the centering scheme is before building your neural Bayes estimator. But what I will say is, if you're interested in sort of incomplete data analysis using neural Bayes estimators, then my colleagues have an interesting paper on arXiv that came out just this year. Okay, so the question was, how can we adapt neural Bayes estimators for these types of centered data? It turns out it's really, really easy to do that. So rather than training a neural Bayes estimator, supplying it the data Z, we're actually going to supply it both Z and this one hot encoding vector that well, it encodes the centering information, right? So for every sampling for every entry to the matrix Z, we have I. It has value 0 if that point is not centered, and 1 otherwise. Okay, and we design a neural network architecture that can take this concatenated vector in as an input and spit out a parameter point estimate as an output. Okay. So there is a bit of sort of technical details here about standardization of the margins and the choice of centering threshold. In the interest of time, I'm going to skip over these and just show you really that these things will work very well in practice. So I'm going to just talk quickly about 3 process models that we were working with in the paper. We consider a few other ones, but here I'll just show the results for free. So one very, very popular model from the spatial streamal dependence literature is the max stable process. Inference for max stable processes is really sort of well, there are a number of papers in the literature and that have come out over the last 20 to 30 years talking about inference for these types of processes. It's very, very difficult. So we wanted to take this particular process model and run away with it and show that actually, if you use these neural Bayes estimators, we solve all the computational problems that other people may have. So we use max stable processes. We use something called an inverted max stable process, which is the pointwise reciprocal of a max stable process. And we also look at inference for something called a random scale mixture process. Now, the reason I've given the equation for this on the slide is that I will come back to talk about this because this is the process of interest in our comparison a bit later on. So they have this interesting sort of formulation. You have a process W, which will be a Matern-Gaussian process. It's a process that exhibits what's called asymptotic independence. We specify the margins of this are heavy-tailed and that they have the same heavy-tailed behavior as this random variable R. We take the product of both of these things raised to these two powers, right? So we have R to the power of delta and W to the power of 1 minus delta. Now, delta is an interesting parameter. It determines whether or not the overall process Z, the random scale mixture, whether or not that exhibits asymptotic dependence or asymptotic independence. And in the interest of time, I won't bore you with the details of asymptotic dependence. If you're interested in extremes, this will be something you're familiar with already, I would hope. So the parameter delta, if it's larger than a half, then the process is asymptotically dependent, asymptotically independent otherwise. This is a particular parameter of interest when using these sort of models. So we set up a simulation study. In this case, I'll focus on the max stable process and the inverted max stable process. In these cases, I'm going to apply censoring with a 90% quantile taken as my censoring level. Now, both of these processes are determined by some parameterized variogram. It has a range lambda and a smoothness parameter kappa, which I place uniform priors on. And in these cases, what I'm going to do is simulate 200 independent replicates of these processes on a 16 by 16 spatial grid. Because my data is on a regular spatial grid, that inner neural network in my neural Bayes estimator is going to be a convolutional neural network. And what I'm going to do is I'm going to compare the efficiency and the efficacy of a neural Bayes estimator for sensor data with the competing likelihood-based approach, which would use a censored pairwise likelihood. So this is a pseudo likelihood. It is pairwise. You take all possible pairs of sampling locations and take the product over all of those pairwise densities. That is what your pseudo likelihood would be, and that's what you would optimize to find your range and smoothness parameters. Now, in particular, I consider two versions of this pairwise likelihood. CPL infinity, this is where you take all possible pairs. CPL free, this is where I only take pairs of locations that are within 3 spatial units of each other. So this is a slightly more efficient estimator than CPL infinity. Okay, and I train my neural Bayes estimator for this particular problem. So with that specified censoring level of tau is equal to 0.9. Again, I have a single neural Bayes estimator for each of these two process models, for MSP and the inverted max stable process. But then I can evaluate that neural Bayes estimator for test parameter sets and for test data sets. So I have 1,000 test parameter sets that I generate from my prior. I get my data and they go straight into the neural Bayes estimator without having to retrain that estimator. Of course, for the censored pairwise likelihood, I have to optimize that for every single new data set it encounters. So of course, this takes quite a considerable amount of time. And here what I'm showing then on the slide, then in these tables, these are the marginal test risk, which essentially give you the accuracy of the neural Bayes estimator in these cases. So the left-hand side, we have the max stable process, the marginal test risk for that lambda estimate, and then for the kappa estimate as well. And similarly for the inverted max stable process on the right-hand side. And in all the cases, you can see the neural Bayes estimator provides lower marginal test risk, provides more accurate estimates of these parameters relative to the competing gold standard likelihood-based inference approach. We can also visualize this. So here I'm plotting the empirical sampling distributions of the estimators for a single true parameter vector. So on the left-hand side for the max stable process, I generate a kappa and a lambda from the prior, that's the green point here. And then conditional on that, I generate 1,000 test data sets. Each test data set, I get a parameter point estimate out from my estimator. And that's what's plotted here on the slides in these joint sampling distributions. So the brown points come from the neural Bayes estimator. The blue points come from one of the censored pairwise likelihoods, the more efficient one. The black points come from the most inefficient censored pairwise likelihood. What you can see is for the neural Bayes estimate, these points are more tightly clustered around the true value. The sampling distribution has much lower variance for the neural Bayes estimator than the censored pairwise likelihoods. Okay, so neural Bayes estimators in this case, they give large improvements in statistical efficiency relative to the gold standard likelihood-based approach. They're also much faster. So our neural Bayes estimator, because we're exploiting GPUs, it takes 1 millisecond, I think that is, 0.0016 seconds to get a parameter point estimate out, whereas the censored pairwise likelihood takes between 2 to 10 minutes to optimize. Okay, now in the paper, we don't just focus on these max stable processes, we also consider this random scale mixture and the Pareto process, and we show similar sort of results in these cases. And this is great. Now we've trained these neural Bayes estimators, we'll be able to use them again for new data sets. However, the key limitation here is because at the start we set this centering threshold at 0.9, this centering level, anybody who wants to use the neural Bayes estimators we trained would have to use exactly the same centering level. Now we can alleviate that issue by randomly generating a centering level during training the neural Bayes estimator by placing a prior on it. We talk a bit about that in the paper. I won't talk about that now in the interest of time. We also have similar results as we had for the invariance of the Bayes estimator with respect to the spatial configuration and the prior place on that. We have a similar result for the prior place on this centering level as well, which is a really nice theoretical result we included in that piece of work. Probably what I can do is go through the application very quickly. I won't have time to talk about the comparison study at the end, but I think this really sort of is my mic drop conclusion to this talk, and I think it's important I give it. So our data application for the censored data paper, we were looking at monthly Saudi Arabian PM2.5 concentrations observed over a very high resolution spatial grid that incorporated not just Saudi Arabia, but the entire Arabian Peninsula. So we have data arranged on a 242 by 182 regular spatial grid, roughly 20 years worth of data. And rather than just fitting a model over the entirety of this spatial domain, I took a similar approach as I did with the sea surface temperature data. But what I'm going to do is use a moving window approach where I essentially fit a model to every window, 4x4 window, 8x8, 16x16 over the entire spatial regular grid. So in total, you end up with about 130,000 spatial process models that you want to fit. You know, obviously, in a typical application, you won't want to do this because it's a bit pathological, but you know, we really wanted to showcase the computational speed ups you get by using a neural Bayes estimator in this setting. Now, for each of these windows, we fit an anisotropic random scale mixture process with 90% censoring. This particular process model has 5 parameters. I'll only really focus on the range and that delta parameter. And again, the neural Bayes estimator is amortised. Now in this case, it's amortised with respect to the loss function, but to the spatial grid. So because I have 4x4, 8x8, 16x16 grids, there are 5 estimators that I need to train to complete this application. Takes roughly between a day and 3 days to optimize these things, but then of course querying the estimators is incredibly fast, and querying them takes between 1 to 4 milliseconds to achieve. Okay, and just to give you a sort of back of the envelope comparison of the speed ups you gain. So if you were to use the full censored likelihood-based inference approach, we estimated it would take you about 1,000 years of computation time to do this application. And actually the neural Bayes estimator is about 10 million times and faster. And as we showed in the simulation study, it's also much more efficient as well. Okay, so here's just an illustration of some of these results. Each of these pixels, this is a single model fit. And on the left-hand side, we have the range parameters, lambda, and on the right-hand side, we have this delta parameter that determines asymptotic independence versus asymptotic dependence. And this is where the window is 4x4. we could smooth over that and look at a 16 by 16 spatial grid instead. One of the really nice sort of things you find here is that you have within the sort of center of the of Saudi Arabia, you have these green areas. The delta parameter is larger than a half, so that implies that you have asymptotic dependence in the PM 2.5 concentrations within land. As you move towards the coastline, it moves towards a regime where you have asymptotic independence. So there's a nice bit of sort of an inference you can do with this particular application. But of course, what we really wanted to show was that you can fit millions of models very, very fast. Now, in this particular piece of work, rather than using the credible intervals estimators that we developed in the first paper, here we just did bootstrap-based uncertainty assessment. So for each of those pixels, I did a bootstrap where I take 1,000 replicates, I refit the model to each of those replicates. So in total, we have 130 million models that had to be fitted for this particular paper to exist. And of course, that's a lot more than any comparable application of spatial extremes. So we were very, very happy with this particular result. You know, this is about a week's worth of computational time in total. So very, very impressive. And one of the really nice aspects of this particular piece of work, which I sort of didn't put in the slides, is, again, not to belabor the point, but these estimators are amortised. And what that means is anybody who wants to reuse them for this particular process model can do. And actually, in a follow-up paper that went up online this year by Raphael Hughes, Jenny Wadsworth, and Thomas Opitz, they took the estimator that we trained from this particular paper and they reapplied it for UK precipitation extremes, completely different environmental process, completely different spatial domain. No need to retrain the estimator. They could just download what I had put on the internet and applied it to their new data set and get parameter estimates out within milliseconds. So of course, very, very impressive takeaway there. I will skip over all of this details of the comparison study. That paper is in the works. Will hopefully be up online in a couple of months' time, but watch that space for this. Essentially, what we're doing is comparing different methods, different techniques for sparse approximations for Gaussian processes, different Bayesian inference methods for random scale mixtures. The conclusion is that neural estimators are incredibly fast compared to standard MCMC type approaches. So to wrap up the talk as a whole then, I've talked a bit about likelihood-free estimators for spatial extremal dependence models. We have neural Bayes estimators for irregular spatial data, and then neural Bayes estimators for censored data, in particular peaks over threshold type models. These are really interesting types of estimators. You get the benefits of the computational speedups relative to gold standard likelihood-based approaches, and in some cases, you also get the statistical efficiency gains, particularly where your only competitor is a pseudo likelihood based approach, as in the case of the max stable process model. Now these sort of these neural Bayes estimators, these are all available in Matt's packages. So there is a Julia package, neural estimators. There is a lovely vignette for that and documentation for that available online. Now, if you don't know Julia, don't worry. There is an R interface to that package that works extremely well as well. Again, with a lovely vignette on CRAN. I recommend you go away and take a bit of a look at that. The censored neural Bayes estimator. I have a separate GitHub repo that has all of that code in it. But actually, since writing these slides, that has now all been implemented directly in the neural estimators package anyway. So you can get that from both of those packages. As I touched upon a bit at the start, right, really I focus here on spatial extremal dependence modeling, but it doesn't necessarily have to be. And in fact, if you're interested in multivariate modeling extremes, you can use these neural Bayes estimators anyway. So some colleagues have got this really interesting paper up online this year looking at using neural Bayes estimators for modeling bivariate extremal dependence. There's new papers up online as well looking at spatiotemporal modeling of extremes. I'm quite happy to link you to that if you drop me an email afterwards. As I mentioned, this big comparison study is coming up soon. One of the sort of key bits of further work that we want to do with this, I touched upon, all I really spoke about was parameter point estimation. So there's a question of how can we use these neural estimators to do full posterior inference? We have some bits and pieces in the work. Again, watch this space, and all of that will be forthcoming hopefully in the new year. So some references. I guess this is probably the key slide I want to end on. We have the JMLR paper on censored inference, and the JCGS paper on irregular spatial data as well. Of course, Matt's collection of more interesting papers as well on the standard likelihood-free parameter estimation with neural Bayes estimators, and this incompleted data analysis, which came out this year as well. And yeah, I'll end there. I'm happy to take any questions. Appreciate there's not much time, but if you need to go, feel free to drop me an email after the talk. Yeah, thank you very much.
Thanks, Jordan. We are running out of time, but we have a very nice question from Dan. I'm not sure if Dan wants to speak up. Otherwise,
Oh, Mike.
okay. Yeah, so basically, he's asking if you can comment on the suitability or possibility to extend the neural Bayes estimator to models with high dimension of parameters, or more complicated models where the parameters are not fully identifiable.
Yeah, so the second point about identifiability is not necessarily okay. I can't really touch upon that because that's not something I've really thought about. But what I will do is answer the point on the dimensionality of the problem then. So in the works I talked about, we went up to 5 parameters, right? Okay, so this is another sort of limitation of neural Bayes estimators in there as they currently stand, is that they can only really be applied to small dimensional parameter sets. So we push things up to 5 in these papers. I believe in the original American statistician paper, they went up to 8 to 10 parameters, and that was for the conditional spatial extremes model. And normally that's okay for the types of models we want to work with in spatial extremes, but yeah, there is a question of how we're going to extend this to more high dimensional problems. I have some ideas in mind. Generally, I think the approach you want to do is to break this up into sort of smaller problems. So one of the ideas we had was to try and build a Gibbs sampler using neural Bayes estimators. And in fact, there was an interesting piece of work recently that came online. I haven't had a chance to read the paper yet, and I couldn't comment on who the authors are, but they had a similar approach where they do amortised inference for spatiotemporal extremes using a Gibbs sampler. So rather than trying to do inference for the entire parameter set, you try and do inference for one of the parameters, condition on the rest of them, and sort of do this in a sequential fashion. That's probably the approach that I'll be taking to try and extend these neural Bayes estimators. But yeah, it's a limitation we have at the moment, but hopefully it won't be for long.
Mm-hmm. And the second part of Dan's question is also quite interesting. He's asking if, in that case, if that would be meaningful to look at like means, like univariate quantiles means medians, if neural Bayes estimator would be relevant in such cases for like more complicated models.
So I'm not sure I understand exactly what you mean. So so you can define neural Bayes estimators that target these summary statistics, yes, means in quantiles. I mean, in our extremes paper, we, rather than build a neural Bayes estimator to target parameters of a model, we target these return levels. So it certainly is possible. But in those cases, really, you are thinking about these summary statistics as a parameter in a model. I mean, if you take, for example, a Gaussian random variable, you can parameterize it and it is typically parameterized by the mean and standard deviation. It's sort of like, you know, thinking about a model where the parameters of interest are these means and standard deviations, rather than, you know, doing a fully non-parametric type approach. We do as well have there is functionality in the neural estimators package to target quantile functions. So I talked a little bit about neural Bayes estimators to target credible intervals. So a vector of posterior quantiles, but we do have some methodology that would allow you to target the entire quantile function as well, which maybe answers the question. I'm not too sure.
Are you having time to stay for one more question, Jordan?
Yeah.
Okay, let's ask one more question from Lucas. So for the graph neural network, how do you build an adjacency matrix to create the graph for point processes? Like how would be considered as a neighbor in that case?
Yeah, so there's a few ways of doing it. One of the things that we did was set a maximum distance. Okay, so we're getting onto the sort of technical points that I skipped over a little bit. So there's a point here that all of the data that we're generating, well, in terms of the sampling locations, are constrained to a unit interval. So we only generate sampling locations on a unit interval, and we specify a maximum distance that determines that adjacency matrix. Now, it doesn't matter what that maximum distance is, because if you have enough layers in your graph neural network, you're still going to pass information on from node to node, regardless as to whether or not a sampling location is within the neighborhood of another node in that first layer. We considered a few ways for constructing the adjacency matrix, or defining neighbors at least, in the paper. I can't quite remember exactly what we sort of advocate in the end. You know, we tried k nearest neighbors, sort of a random sampling of k nearest neighbors within pre-specified disk, a min-max ordering, so something very, very popular in the Vecchia approximation literature. So there's lots of ways of doing it, and actually, when you build these neural estimators, you pick and choose, right? As with any sort of deep learning type modeling approach, you want to be doing some form of architecture optimization. Here we have the nice benefit of not necessarily having to worry about you know, having finite samples for training the neural estimator anyway. You can have an incredibly complicated architecture, and you can just generate more data for training the neural estimator, as long as you have the computational resources to do so. The adjacency matrix is sort of implicit actually in this propagation module as it's described here on the slide. So rather than having a fixed adjacency matrix that might have edges determined by the sort of Euclidean distance between sampling locations, here you can see I have this weighting function here, and the weighting function, okay, you could, you know, it could spit out exactly the Euclidean distance, but here we actually have this multi-layer perceptron that sort of gives you a bit more flexibility in terms of those weights. Yeah, I mean, if you're really interested in the technical details, I'm very happy to talk about these things offline. But the paper certainly has much more details that I can give in just via Zoom essentially. So hopefully that answers the question.
Yes, thanks a lot, Jordan. So there are more questions for you, but I think in the interest of time, you will be very happy to receive emails for the questions, right? Yeah. So if nobody else wants to speak up, let's thanks Jordan again, and maybe see you in next year.
Yes.
Thanks, everyone.
Thank you for coming, everyone.
Thank you, Jordan. You should give a tutorial online how to do all the codes.
I do have, actually, the slides for these are on my website. I do have, I believe, a tutorial for doing neural estimators somewhere. I mean, if it is of interest, I'm happy to give a quick sort of run through of the package. Potentially that would be, it wouldn't fill an hour, but we could do that in collaboration in sort of, if somebody else has a package that they want to showcase, maybe we could do like half an hour each. I don't know. But yeah, happy to do whatever.
Okay, thank you so much, Jordan. Bye bye.
Thank you.
Good. Have a nice holiday, everyone. Those that celebrate.
Thank you.